Alright, Alan, this is take one. This is Matt. I'm going to be doing a quick coverage of some of the basics of electricity on this video. I haven't decided yet everything about it. It's pretty unprofessional. You can see we're doing this on a piece of notebook paper in a kitchen with a table that needs to be cleaned off and everything else. So, but let's get at it. I'm going to do my best to make the video to where you can see things, to where things are explained clearly and you can make sense of what's going on. So the first question is, what is electricity and why do we call it electricity? And the easy part about it is just keep the explanation as simple as possible. I've drawn here a model of a copper atom. And this copper atom basically is only here so that you can picture what's going on at the outer shell. Okay? Anytime that you have any kind of molecule, you probably learned in chemistry well before this, that you have a nucleus. Inside the nucleus is all your positively charged protons, all of your neutrons, which are neutrals, and then as you go out into the shells surrounding that nucleus, you have electrons, which basically stabilize themselves at different energy levels. Here you see the rings drawn for the first ring, first shell, second shell, and so on. I haven't drawn all the rings here. I don't even remember how many rings are in a copper atom. It really doesn't matter. The main point about copper is a good conductor. And why is copper a good conductor of electricity? And the answer is because copper only has one valence shell electron. So this right here, the outermost shell of any atom, is always going to be referred to as your valence shell. And if you only have one electron in the valence shell, first of all, the magnetic forces that are bonding this electron to this nucleus are going to be much weaker than the magnetic forces that are bonding these electrons in this closest shell to the nucleus. Once you get to the outermost shell, the forces are much weaker, and what can happen is you can excite this electron with enough energy to make it move away from that particular molecule. Now what I've drawn in this second picture that you've got here is just picture a copper wire. It can be any copper wire, it can be one big solid sheet of copper wire, it can be a twisted braid of copper wires. The important part is that all of the metal in here is all copper, it's all conductive, and these are designators. The little E- is my designator for electrons. So what's going on with these electrons? Well, basically what you have in here is this whole thing is comprised of a whole bunch of tiny little molecules of copper, and they fill this entire conductor up. If we want to impart electricity and make electricity move across this conductor from left to right in our diagram, we would need to induce what's called a voltage. Okay? A voltage, which you've heard the term many times, but how much you may know about the actual application of it, I'm not sure. Voltage is basically equal to potential. And what kind of potential? It's electrostatic potential. Basically what you're doing here is you are setting up some kind of external force that when you connect it to here, it's going to make an effort to push these electrons from one side of the conductor to the other. What happens to the copper atoms in here? Do the copper atoms move with them? No, the copper atoms stay. And if you could just picture that here you have another copper atom right next to this, and here's your electron shells. Once you get to the outermost shell here, this electron right here, these guys just break away from these molecules and just sort of move freely within the conductor. And they will move with more force and more energy the more voltage that you have there. Okay, it doesn't necessarily mean that they move faster the more voltage you have there, but they do move with more force the more voltage you have there. We could get into formulas for charge and things like that, but the important thing for you to understand is where are these electrons coming from and where are they going to, why are they moving. Electricity, I read in a book, the Stanley Gibilisco book, Teach Yourself Electricity and Electronics, that you can picture electricity like a bunch of people standing next to each other, and in a circle passing tennis balls. One person hands a tennis ball to the person in front of them, at the same time they reach behind them and pick up another tennis ball from the person behind them. And this exchange goes on and on and on in a loop. And as these people pass these tennis balls in a loop, basically there's potential for work to be done amongst the movement of those tennis balls. And we're working with electrons here, so keep in mind these electrons are negatively charged particles. So what this means is that they are not only particles that have energy built into them because they are moving, because they have velocity, because they have energy that they're moving with, but also because they have a charge, they are magnetic. So remember, that means that these negatively charged particles are magnetic. For our purposes, and I'm not going to get into the physics of how everything works, but for our purposes, electricity and magnetism are joined in certain places. Not every place are we going to talk about electricity and magnetism together, but we will talk about electricity and magnetism together often enough that you will need to remember that when there is a movement of current, that is electrons moving through a conductor, through a load, through a resistor, whatever it happened to be, that when those electrons are moving, they also are magnetic charges moving. And that can impact greatly the way things are happening on any kind of system that you happen to be looking at, or in our case, testing on.